Today we are going to discuss the nature of Hamiltonian for particles moving in spherically symmetric potentials. There are many situations where the potential acting on the particle is spherically symmetric, like the case of electrons in atoms. An understanding of this topic will help us to easily study the angular momentum and hydrogen atom problems. In a spherically symmetric potential, the potential energy V depends only the distance of the particle from a fixed point. That is, V is a function of r rather than of x, y, z. In such situations, it is advantageous to represent the Schrödinger equation in spherical polar coordinates owing to the symmetry of the physical situation. Consider a point P in spherical polar coordinates. Then the length of the vector from the origin to the point P is given by r equal to square root of x square plus y square plus z square. Theta is called the zenith angle, which is the angle between this radius vector and positive z axis, and phi is the phi or the azimuth angle is the angle between the projection of this radius vector onto the xy plane and the positive x-axis. And with all these expressions connecting the spherical polar coordinates and the Cartesian coordinates, we can actually write the Schrödinger equation in spherical polar coordinates like this one. So those who are interested to know how to get this expression, they can find the complete derivation in the textbook Quantum Mechanics by Ajay Ghatak. Like what we have seen for Cartesian coordinates, here also psi must be normalizable, and psi and its derivative must be continuous and single valued at each point r, theta and phi. The advantage of writing Schrödinger equation in spherical polar coordinates is that it can be separated into three independent equations, each involving only a single coordinate. Hence, the wave function psi r theta phi has the form of a product of three different wave functions: capital R, which depends on the radial position alone, and capital theta, which depends on the angle small theta alone, and capital phi, which depends on the angle small phi alone. The function capital R basically describes how the wave function psi varies along a radius vector from the origin, with theta and phi kept constant. Similarly, the function capital theta describes how the wave function psi varies with the zenith angle theta along a meridian on a sphere with r and phi constant. And the function capital phi describes how the wave function psi varies with azimuth angle phi along a parallel on a sphere with r and theta constant. With this equation 2, various partial differentials become complete derivatives like this one. Instead of dou psi by dou r, we can write it as a complete derivative of capital R by dr, keeping the other two constant, because these two constants are not depending the variable r. Similarly, we can write the partial derivatives of psi with respect to theta and phi also as complete derivatives of theta and phi. So, if we substitute equation 2 in equation 1, we get an expression like this one. It's a long expression, but upon further simplification, we get sin square theta by r d by dr r square d capital R by r plus sin theta by theta d by d theta sine theta d theta by d small theta plus 1 by phi d square capital phi by d phi square plus 2m r square sine square theta by h cross square into e minus v equal to 0. You can see that the third term in this expression is a function of azimuth angle phi alone, whereas the other terms are functions of r and theta only. So let's rearrange this expression like this one. So now the left hand side of this equation does not have any terms involving phi, while its right hand side has only phi dependent term. This equation can be correct only if both sides of it are equal to some constant, since they are functions of different variables. So let's call this constant as m square. Thus, after rearranging this, we have an expression like d square phi by d phi square is equal to minus m square phi from the right hand side of this equation, and we have equating the left hand side of this equation to the same constant, and then rearranging we will get an expression like this one. Just rearrange this one after equating it with m square, then this one will be resulted. Again, in this sixth equation, different variables appear on each side, and hence it demands that both sides must be equal to some constant, let's say lambda. Thus we get two more equations as 1 by r square d by dr, r square d capital R by dr plus 2m by h cross square into e minus v minus lambda by r square into capital R is equal to 0, and 1 by sine theta d by d theta sine theta into d capital theta by d theta plus lambda minus m square by sine square theta into capital theta equal to 0. So these two equations are resulted from the equation 6 by equating the left hand side equal to some constant lambda and the right hand side equal to some constant lambda, and we did that because the left hand side is a function of the variable small r and the right hand side is a function of the variable small theta, where these two variables are independent variables. So essentially you have one kind of function on left hand side and another kind of function on right hand side, and this is equated here, and this equality is possible only if these entire things are equal to some constant. Now after rearranging, these are the two expressions that we get. Thus what we have seen is that the three-dimensional wave equation is reduced to three one-dimensional wave equations given by the equations 5, 7 and 8. Each of these is an ordinary differential equation for a single function of a single variable. Only the equation for capital R depends the potential energy. Now let's try to find out the solutions for each of these three equations. So first let's try the solution to the capital phi equation. The phi equation suggests a solution of the form a e raised to plus or minus im phi. Since capital phi is a component of the complete wave function psi, the condition of psi, that is psi must be single valued at a given point in space, must be obeyed by phi 2. That is, capital phi of phi must be same as capital phi of small phi plus 2 pi, because changing the angle phi by 2 pi times essentially gives the same point in the space. That means the constant m can have only integer values. So the solution to phi equation is a e raised to im 2 pi equal to 1 with the values of m are restricted by these values, because only for these values of m this equation will become 1. So the solution to the phi equation is given by a e raised to, so the solution to the phi equation can be written as a e raised to im phi with the values of m restricted to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Actually this plus or minus symbol is transferred into the values of this m, so that we write this as simply a e raised to im phi. And this constant m is usually called the magnetic quantum number. To know the magnitude of the constant a in this expression, we have to normalize the wave function. That is, you have to integrate it from 0 to 2 pi, because the angle phi can vary maximum up to 2 pi. So this integral must be 1. Substituting for phi from this equation gives us that a equal to 1 by square root of 2 pi. Hence the normalized solution can be written as capital phi m of phi is equal to 1 by square root of 2 pi e raised to im phi with the integer values for the magnetic quantum number m. Now we have put a small subscript m along with this wave function capital phi, since this wave function depends on this quantum number m. So now let's try to solve the theta equation. So to solve this theta equation, let's introduce a new variable such that z is equal to cos theta, and with this the equation 8 can be essentially written like this. So with this transformation, the equation on theta variable is transformed into an equation in the new variable z. Now this equation can be identified as the associated Legendre equation if the constant lambda is equated to L into L plus 1, where L is an integer constant. Now the condition of associated Legendre function demands that the integer m can have both positive and negative values, like what we have seen in the solution of phi equation, but its maximum value is limited by the value of the constant small l, such that m is less than or equal to this new constant small l. So the upper value of the magnetic quantum number is limited by plus or minus l, this new quantum number. So the possible values for the magnetic quantum number is 0, plus or minus 1, plus or minus 2, etc. up to an upper value of plus or minus L. Now m equal to 0 in equation 9 leads to the Legendre polynomial. So the solution to this equation 9 are the Legendre polynomial when m is equal to 0 and associated Legendre polynomial PLM of z when m not equal to 0. Therefore the normalized solution to the theta equation can be written as capital theta is equal to some normalization constant into this associated Legendre polynomial. So instead of z, we have written it in terms of the angle cos theta. So you can see that the eigenfunctions for the theta equations are the associated Legendre polynomials, and this is a normalization constant which can be estimated from the normalization condition of associated Legendre polynomial. And we identified these theta equation to uh, this theta equation as the associated Legendre equation with the substitution that the constant lambda must be equal to this constant L into L plus 1, and this L can have values 0, 1, 2, 3, etc., 0 or positive integer values. And this is also a quantum number associated with the particle moving in the spherically symmetric potential, and this is usually called the orbital angular momentum quantum number. We have seen the solution to these two parts of the wave functions, the capital phi part of the wave function and capital theta part of the wave function. And the capital phi, we have seen a function which is orthonormal to the azimuth angle phi, and the solution to the capital theta part was the associated Legendre polynomial PLM cos theta, which is orthonormal with respect to the polar angle theta. And we take the product of these two to obtain functions of two angles theta and phi which are orthonormal over the spherical surface, and these are called the spherical harmonics given by the expression ylm theta phi is equal to some normalization constant into the product of the solution to the phi part of the wave functions and to the theta part of the wave functions. The first few spherical harmonics are given by these expressions. For example, y00, in this case both these quantum numbers L and M have its smallest possible values, and that is given by square root of 1 by 4 pi. And if you substitute the allowed values of the quantum numbers for L and M, we can have the different spherical harmonics functions. And visual representations of the first few real part spherical harmonics are shown here. The blue portions here represents the regions where the function is positive, and the yellow portions represent where it is negative. The distance of the surface from the origin indicates the absolute value of ylm theta phi in angular direction theta phi. So these pictures will give you an idea how the wave functions of the particle looks like in a spherically symmetric potential. So the product of theta and phi part of the wave function will looks like these structures for the different values of angular momentum quantum number L, and for each of the angular momentum quantum number there are different possibilities for the magnetic quantum numbers, and for each of that the shape of these functions are something like this. So this will help us to identify the nature of the orbitals. For example, if you study the hydrogen atom problem or any problems related to a spherically symmetric potential. Now we have one more part to solve, that is the radial part of the equation given by this expression. So the only difference what we have done here is that in place of lambda we have written L into L plus 1, because in the solution to the capital theta equation we saw that the capital theta part will become the associated Legendre polynomial when the constant L is equated to small l into L plus 1. So with that substitution, this is the radial part of the wave function. To solve this equation, the explicit form of potential is usually required because the potential energy term appears in this equation. Note that the potential energy V is a function of R alone in spherically symmetric potentials. And now let's make a substitution. Capital R of R is equal to a new variable chi of R by small r, which will make this equation looks like this. Equation is transferred from the capital R to chi of R. Now this is quite easy to identify this equation. This is the form of a one-dimensional Schrodinger equation of a particle of mass m moving in the direction of small r in a field of effective potential given by V of r plus L into L plus 1 h cross square by 2m r square. The additional potential L into L plus 1 h cross square by 2m r square is a repulsive one, and it corresponds to a force L into L plus 1 h cross square by m r cube. Now if we write the centrifugal force, we know the expression for the centrifugal force, which is mr omega square, in terms of the orbital angular momentum capital L. We have an expression like this: mr omega square equal to the square of the angular momentum divided by mr cube. Now if we compare this centrifugal force with the force due to this additional potential term, you can see that L square corresponds to small l into L plus 1 h cross square. So you can easily identify that the constant small l is associated with the orbital angular momentum, and hence it is called the orbital angular momentum quantum number.